Hello again, physics fans. My name is Varun Yarabarla. This is my video report on Lab 4, Rope Physics Spring Mass Lab. The problem that had to be dealt with was examining the motion of a spring mass that was oscillating while swinging in an arc. The point of this lab is to quantify the motion of a mass attached to a spring and tracker using a video provided, and through the application of the momentum principle and the energy principle, the motion was predicted and analyzed through VIDLE. Once this was done, a comparison had to be made between the predicted motion for the model and the actual data extracted from tracker. The motion of the mass was similar for both in the x and the y directions. The results were that the predicted motion of the mass followed the same pattern as the data received from tracker. The positions did not match up slightly due to when the drag force caught up to the spring force and slight round-off errors. There are two main principles that are applicable to this lab: the momentum principle and the energy principle, as these are the two models relevant to the physical system. Once the video was in tracker, I placed the calibration stick so that it represented the spring's relaxed length at 0.7 meters. I put the origin at the point where the spring was attached. After pinpointing all the point mass locations, I took the x and y positions shown here on the right and placed them into a CSV file that can be used and read in my code, seen here, in columns A and B. The mass of the ball is 0.402 kilograms. The initial position is shown here, and the initial velocity is 0 meters per second, while the start time is 0 seconds. Next, I use these equations to solve for the spring constant, the change in stretch, and the stretch length of the spring. Then I put each of these values into my code, as you can see here. Using the formulas for omega and period, I solved for the spring constant, which came out to be 6.88. L initial is the relaxed length without the mass and was solved to be 0.128 meters. L is the length of the spring with the mass. Here, S is the stretch of the spring, which is calculated. The energy principle is used to calculate all the initial energy values. In the while loop, the time is set to equal the length of the tracker video, 9.307 seconds. Gravitational force is mg. Here's the force of the spring using Hooke's law. The net force is gravitational force plus the spring force. The momentum principle is used to update velocity and the position. Kinetic energy is 1/2 mv squared, gravitational potential energy is mgh, and spring potential energy is 1/2 ks squared. Here are all these energy calculations which are updated. Now you can see my model in Python. The red ball is representative of the data from tracker, and the blue is of the computational model. It is clear that they are following the same path. They are very close to each other. This is the position data in the y direction. It is very close, so my computational model is a good predictor of the original motion of the mass. The reason for the slight discrepancy between the two lines in the graph on the right is due to the fact that the drag force catches up with the spring force, and there is possibly some slight round-off error during the computation. In my code, I made a graph to show the change in kinetic energy, the change in spring potential energy, and the change in potential gravitational energy. When I run my code, this is what the motion looks like on the left once again, but on the graph here on the right is different. It shows all the various energies involved. The red is the kinetic, and the green is the potential spring energy. The blue is the gravitational potential energy, and the yellow is the sum of the total energy. Now let's answer the questions. Question 1. The work done by the surroundings is equal to the change in energy, but because there's nothing in the surroundings with the Earth, the spring, and the mass being in the system, the work by extent, the change in energy, should be 0. There is no outside work done on the system, so W equals delta E. Delta E on the graph is from earlier, shown here. The yellow one is 0, which makes sense. Question 2. These are the two oscillation graphs. The period of oscillation for x is 1.7 seconds, and for y it is 1.52 seconds. It is clear that the x and y oscillations differ by 0.2 seconds. This is because, as seen here, the motion of the spring is elliptically shaped. It's elliptically shaped and slanted downwards. This shows that it takes more time to move one cycle in the x direction than in the y direction. That being said, the 0.2 seconds is not extremely significant.